All right, we're now going to begin the lecture on chapter 9. This is 9.1. All right, chapter 9 focuses on conservation of momentum. So we're going to, and collision. So we're going to start with defining momentum. To be specifically, we're talking about linear momentum right now. All right, so we've talked about systems that contain multiple objects. And here I've denoted the system boundary, and the two objects inside are part of the system. So now we're going to consider what if these two particles or objects have velocities. And what if they interact with each other, but nothing outside the system? So we will allow interactions within the system, but not across the boundary. All right, so we've talked about this a lot in terms of energy already, and that means that we're not going to lose any energy, but we have to be careful with that because we can lose mechanical energy, right? We can convert it to forms that are not easily transferred back to mechanical energy like heat, right? So that's why we went through all the types of energy so that we can be a little more specific right now. So mechanical energy isn't necessarily conserved here. So we want to talk about what is conserved. So the only thing that they can interact with is each other because they can't interact with anything across the boundary. And we know by Newton's third law that the force on 1 due to 2 is equal to minus the force on 2 due to 1. And let's apply Newton's second law to that. So we have M1A and M2A. Let me write it, instead of writing it with absolute values, let's write it this way. Oop. Since they're equal in opposite directions, it wouldn't let me scroll there. Since they're equal in opposite directions, I can write it as a vector sum that's equal to 0. So let's do it that way. Because that gets me where I want to be. So by Newton's third law, if there's no interactions across the boundary and they're only interacting with each other, and I know these forces are equal and opposite, then add to 0. And we're going to take that to the next step here by applying Newton's second law. And then we're going to go a step further and apply our definition of acceleration, right? We know that the acceleration is the time rate of change of velocity. So we can go further and call this dv dt for each acceleration. And since the masses are constant, we can bring them, so at this line, we're applying the definition of acceleration. And here, the next thing we're going to do is we're going to move m inside the derivative since it's constant. All right, we can do that because it moves across the derivative without any issues because it's constant. It's just like multiplying a scalar times the variable that you're taking the derivative on. Right? So we can now write this as d dt of m1v1 plus d dt of m2v2 equals 0. And now we can see that we can take out that derivative operator and apply it to the whole thing. So we now have that the time derivative of m1v1 plus m2v2 is equal to 0. And what does it mean for the time derivative of something to be 0? That means it's not changing with respect to time. All right, so not changing and that's what we mean by conserved. So this quantity, m1v1 plus m2v2, do I want to set it equal to a constant or just say it's conserved? Is conserved. And this is what we define as momentum. Linear momentum is denoted by P, and it is a vector, right? And it's equal to m times v. And because it's a vector, we can break it into components. So we can have px equal to mvx, py, mvy, mpz, mpc. All right, so this is going to be very useful when we talk about collisions because we can have energy loss during that collision and it's very hard to deal with. We've talked about in the past how spiky a force versus time can look like when two things collide. And it's very hard to know what that looks like. It's hard to determine this exactly. If we know exactly what it looks like, we could take a derivative, or sorry, an integral over that, and we would know values that we could use. But in general, if momentum is conserved, it's much easier. So what else do I want to talk about for momentum in this section? I just want to point out that for Newton's second law, it was originally presented in presentation of momentum. So let's start with what we have. Sum of forces equal to ma, and we're going to do the same thing we did before. So A is dv dt. And we can bring the m in, and we see that we actually have the time rate of change of momentum is what the sum of forces is equal to. So this is the historical presentation of Newton's second law. We tend to do it MA these days. But you also note that that has the assumption that the mass is constant. So if we start talking about a varying mass, like you would with a rocket or something, then we're really going to have to think about this in terms of the momentum changing rather than just an acceleration. And that's where I'm going to stop for this section, and we'll move to the next one.